Chapter 10 Application Layers. Upon completion of this chapter, you will be able to explain how the functions of the application layer, session layer, and presentation layer work together to provide network services to end-user applications. Describe how common application layer protocols interact with end-user applications. Describe, at high level, common application layer protocols that provide Internet services to end users, including www services and email. Describe application layer protocols that provide IP addressing services, including DNS and DHCP. Describe the features and operation of well-known application layers protocols that allow for file sharing services, including FTP, file sharing services, SMB protocol, and explain how data is moved across the network from opening an application to receiving data. On the OSI model, data is passed from one layer to the next, starting at the application layer on the transmitting host and proceeding down to the hierarchy to the physical layer. The functionality of the TCP/IP application layer protocols fit roughly into the framework of the top three layers of the OSI model: application, presentation, and session layers. The application layer is the layer that provides the interface between the applications we use to communicate and underlying network over which our messages are transmitted. Application layer protocols are used to exchange data between programs running on the source and destination host. Some of the most widely known application layer protocols include Hypertext Transfer Protocol, File Transfer Protocol, Trivial File Transfer Protocol, Internet Message Access Protocol, and Domain Name System. The presentation layer has three primary functions: present data from the source device into a compatible form of the destination device, compression of the data in a way that can be compressed by the destination device, and the encryption of the data for transmission and encryption of data upon received by the destination. Some well-known standards for video include QuickTime and Motion Picture Experts Group, Interchange Format, Joint Photographic Experts Group, and Portable Network Graphics. The session layer creates and maintains dialogues between source and destination applications. The session layer handles the exchange of information to initiate dialogues, keep them active, and to restart sessions that are disrupted or idle for a long period of time. TCP/IP application layer protocols. Domain Name System. This protocol resolves Internet names into IP addresses. Bootstrap Protocol. This protocol is a precursor to the DHCP protocol. BOOTP is a network protocol used to obtain IP address information during boot up. Dynamic Host Configuration Protocol. A protocol used to assign an IP address, subnet mask, default gateway, and DNS server addresses to a host. Simple Mail Transfer Protocol. This protocol transfers mail, messages, and attachments. Post Office Protocol. A protocol used by email clients to retrieve email from a remote server. Internet Message Access Protocol. This is another protocol for email retrieval. File Transfer Protocol. A protocol used for interactive file transfer between systems. Trivial File Transfer Protocol. This protocol is used for connectionless active file transfer. Hypertext Transfer Protocol. This protocol transfers files that make up the web pages of the World Wide Web. When accessing information on a networking device, whether it is a PC, laptop, tablet, smartphone, or some other device connected to a network, The data may not be physically stored on the device. In this case, a request to access that information must be made to the device where the data resides. In the peer-to-peer networking model, the data is accessed from a peer device without the use of a dedicated server. The P2P network model involves two parts: P2P networks and P2P applications. P2P applications. A peer-to-peer application allows a device to act as both a client and a server within the same communication. As shown in the figure, in this model, every client is a server and every server is a client. Some P2P applications are based on the Gnutella protocol. They enable people to share files on their hard disk with others. As shown in the figure, Gnutella-compatible client software allows users to connect to Gnutella services over the Internet and to locate and access resources shared by other Gnutella peers. Many client applications are viable for accessing the Gnutella networking, including Bearshare, Nucleus, LimeWire, Morpheus, WinMX, and SoloX. In the client-server model, the device requesting the information is called a client and the device responding to the request is called a server. Client and server processes are considered to be in the application layer. The client begins the exchange by requesting data from the server, which responds by sending one or more streams of data to the client. Application layer protocols describe the format of the requests and responses between clients and servers. In addition to the actual data transfer, this exchange may also require user authentication and the identification of a data file to be transferred. One example of a client-server network is using an ISP's email service to send, receive, and store email. The email client on a home computer issues a request to the ISP's email server for any unread mail. The server responds by sending the requested email to the client. Although data is typically described as flowing from the server to the client, some data always flows from the client to the server. Data flow may be equal in both directions, or may even be greater in the direction going from the client to the server. For example, a client may transfer a file to the server from storage purposes. As shown in the figure, data transfer from a client to a server is referred to as an upload and data from a server to a client as a download. There are three application layer protocols that are involved in work or play every day. There are Hypertext Transfer Protocol, Simple Mail Transfer Protocol, and Post Office Protocol. These application layer protocols make it possible to browse the web and send and receive email. HTTP is used to enable users to connect to websites across the Internet. SMTP is used to enable users to send email, and POP is used to enable users to receive email. When a web address or uniform resource locator is typed into a web browser, the web browser establishes a connection to the web service running on the server using the HTTP protocol. URLs and Uniform Resource Identifier are the names most people associate with web addresses. First, as shown in Figure 1, the browser interprets the three parts of the URL. First, HTTP, the protocol or scheme. Second, www.cisco.com, that is the server name. And third, index.html, that is the specific file name requested. As shown in Figure 2, the browser then checks with a name server to convert www.cisco.com into a numeric address, which it uses to connect to the server. Using HTTP requirements, the browser sends a GET request to the server and asks for the index.html file. The server as shown in Figure 3, sends the HTML code for this web page to the browser. Finally, as shown in Figure 4, the browser deciphers the HTML code and formats the page for the browser window. Entering www.cisco.com in the address bar of a browser generates the HTTP GET message. GET is a client request for data, and client sends the GET message to the web browser to request HTML pages. POST and PUT are used to upload data files to the web server. The POST message is sent to the web server. Included with the POST message is the data that the user submitted in the form. PUT uploads resources or content to the web server. Although HTTP is remarkably flexible, it is not a secure protocol. The request messages send information to the server in plain text that can be intercepted and read. Similarly, the server responses, typically HTML pages, are also unencrypted. The HTTP secure protocol is used for accessing or posting web server information. HTTPS can use authentication and encryption to secure data as it travels between the client and the server. Email clients send messages to the email server configured in the application settings. When the server receives the message, it checks to see if the recipient domain is located on its local database. If it is not, it sends a DNS request to determine the IP address of the mail server for the destination domain. The email is then forwarded to the appropriate server. Email supports three separate protocols for operation: Simple Mail Transfer Protocol, Post Office Protocol, and the Internet Message Access Protocol. The application layer process that sends the mail uses SMTP. This is the case if sending from a client to a server, as well as when sending from one server to another. Simple Mail Transfer Protocol transfers mail reliably and efficiently. For SMTP applications to work properly, the mail message must be formatted properly and SMTP processes must be running on both the client and server. When a client sends an email, the client SMTP process connects with a server SMTP process on the well-known port 25. The destination email server may not be online or may be busy when email messages are sent. Therefore, SMTP spools messages to be sent at a later time.
Post Office Protocol (POP) enables a workstation to retrieve mail from a mail server. With POP, mail is downloaded from the server to the client and then deleted from the server. Internet Message Access Protocol (IMAP) is another protocol that describes a method to retrieve email messages. Unlike POP, when the user connects to an IMAP-capable server, copies of the messages are downloaded to the client application. The original messages are kept on the server until manually deleted. Users view copies of their messages in their email client software. Domain Name Service. The Domain Name Service was created for domain names to address resolution for these networks. DNS uses a distributed set of servers to resolve the names associated with these numbered addresses. Figures 1 through 5 display the steps involved in DNS resolution. The DNS server matches the domain name with numeric address and give the address in numerical values. For example, for www.cisco.com, the numerical value is 198.133.219.25. The client asks for the DNS server the numerical value for the address for cisco.com. Then the DNS server replies to the client the numerical value, and the client receives the numerical value. A DNS server provides the name resolution using the Berkeley Internet Name Domain (BIND). The DNS server stores different types of resource records used to resolve names. These records contain the name, address, and type of record. Some of these record types are A. An end device address, NS, an authoritative name server, seed name, the canonical name or fully qualified domain name for an alias, used when multiple services have the single network address, but each service has its own entry in DNS. MX, mail exchange record, maps a domain name to a list of mail exchange servers for that domain. When a client makes a query, the server BIND process first looks at its own records to resolve the name. If it is unable to resolve the name using its stored records, it contacts other servers to resolve the name. The request may be passed along to a number of servers, which can take extra time and consume bandwidth. Each DNS server maintains a specific database file and is only responsible for managing name to IP mappings for that small portion of the entire DNS structure. When a DNS server receives a request for a name translation that is not within its DNS zone, the DNS server forwards the request to another DNS server within the proper zone for translation. When configuring a network device, we generally provide one or more DNS server addresses that the DNS client can use for name resolution. Usually, the Internet Service Provider, ISP, provides the addresses to use for the DNS servers. When a user's application requests to connect to a remote device by name, the requesting DNS client queries one of these name servers to resolve the name to a numeric address. The DNS client supports name resolution for other network applications and other services that need it. Computer operating systems also have a utility called NSLookup. This utility can also be used to troubleshoot name resolution issues and to verify the current status of the name servers. NSLookup. DNS server is dns-sj.cisco.com, which has an address of 171.70.168.183. The name of a host or domain can be entered at the NSLookup prompt. In the first query in the figure, a query is made for www.cisco.com. The responding name server provides the address of 198.133.219.25. Enter the NSLookup command to begin the manual query of the name servers. The output lists the name and IP address of the closest name server. In this case, the user is in a home network behind a router firewall. The address in the router you are now is NSLookup mode. Enter the domain name www.cisco.com. The output lists all the addresses that the server E144 currently has in its database. Notice that IPv6 addresses are auto-listed. In addition, various aliases are shown that will resolve to www.cisco.com. Enter the exit command to leave NSLookup mode and return to the Windows command line. You can directly query the DNS servers by simply adding the domain name to the NSLookup command. Enter NSLookup command www.google.com. You are now in a different location on a Linux machine. The NSLookup command is the same. Enter the NSLookup command to begin a manual query of the name servers. Notice the output is similar as what you got from the Windows command line. Enter the exit command to leave NSLookup mode and return to the Linux command line. As Windows, you can directly query the DNS servers by simply adding the domain name to the NSLookup command. Enter NSLookup www.google.com. You successfully used the NSLookup command to verify the status of domain names. Dynamic Host Configuration Protocol, DHCP. The Dynamic Host Configuration Protocol service enables devices on a network to obtain IP addresses and other information from a DHCP server. DHCP allows a host to obtain an IP address dynamically when it connects to a network. On larger local networks, or where the user population changes frequently, DHCP is preferred for address assignment. New users may arrive with laptops and need a connection. Others may have new workstations that must be connected, rather than have the network administrator assign IP addresses for each workstation. It is more efficient to have IP addresses assigned automatically using DHCP. As the figure shows, various types of devices can be DHCP servers when running DHCP service software. With home networks, the DHCP server is usually located on the local router that connects the home network to the ISP. Local hosts receive IP address information directly from the local router. The local router receives an IP address from the DHCP server at the ISP. DHCP can pose a security risk because any device connected to a network can receive an address. This risk makes physical security a determining factor or whether to use dynamic or manual addressing. Both dynamic and static addressing have a place in network design. Many networks use both DHCP and static addressing. DHCP is used for general-purpose hosts, such as end-user devices. Static addressing is used for network devices, such as gateways, switches, servers, and printers. DHCP operation. Without DHCP, users have to manually input the IP address, subnet masks, and other network settings to join the network. As shown in the figure, when a DHCP configured device boots up or connects to a network, the client broadcasts a DHCP discover message to identify any available DHCP servers on the network. A DHCP server replies with a DHCP offer message, which offers a list to the client. The client may receive multiple DHCP offer messages. If there is more than one DHCP server on the local network, therefore it must choose between them and sends a DHCP request message that identifies the explicit server and lists offer that the client is accepting. The DHCP server ensures that all IP addresses are unique. Using DHCP enables network administrators to easily reconfigure client IP addresses without having to manually make changes to the client. Most internet providers use DHCP to allocate addresses to their customers that do not require a static address. File transfer protocol. The data transfer can happen in either direction. The client can download or pull data from the server, or the client can upload or push data from the server. The File Transfer Protocol, FTP, is another commonly used application layer protocol. FTP was developed to allow for data transfers between a client and a server. An FTP client is an application that runs on a computer that is used to push and pull data from a server running an FTP daemon. As the figure illustrates, to successfully transfer data, FTP requires two connections between the client and the server, one for commands and replies, and other for the actual file transfer. The client establishes the first connection to the server for control traffic, consisting of client command and server replies. The client establishes the second connection to the server for the actual data transfer. This connection is created every time there is a data to be transferred. Server Message Block, SMB. The Server Message Block is a client-server file sharing protocol developed by IBM in the late 1980s to describe the structure of shared network resources such as directories, files, printers, and serial ports. It is a request-response protocol. The SMB protocol describes file system access and how clients can make requests for files. It also describes the SMB protocol inter-process communication. All SMB messages share a common format. This format uses a mixed sites header followed by a variable size parameter and data component. SMB messages can start, authenticate and terminate sessions, control file and printer access, allow an application to send or receive messages to or from another device. The Linux and Unix operating systems also provide a method of sharing resources with Microsoft networks using a version of SMB called Samba. The Apple Macintosh operating systems also support resource sharing using the SMB protocol.
The application layer is responsible for directly accessing the underlying processes that manage and deliver communication through the network. This layer serves as the source and destination of communication across data networks. Trends like bring your own device, access anywhere, virtualization, and machine-to-machine connections have made way to a new breed of applications, using smart tagging and advanced connectivity to digitize intelligent products from bikes and bottles to refrigerators and cars, and connect them to the internet. We allow people and companies to interact in new and almost unimaginable ways, and over 100 million vending machines, vehicles, smoke alarms, and other devices are already sharing information automatically today. 37 billion new things will be connected by 2020. How a message travels through a network. When an application sends a request to a server application, the message is built by the application layer, but is then passed down through all the various layer functionalities on the client for delivery. As it moves through the stack, each lower layer encapsulates the data with a header that contains the protocols of communication for that layer. These protocols, which are implemented on both the sending and receiving hosts, interact to provide end-to-end delivery of applications over the network. Using the TCP/IP model, a complete communication process includes 6 steps. Creation of the data. The first step is the creation of the data and the application layer of the originating source and device. In this case, after building the web client's request, known as an HTTP GET, that data will then be encoded, compressed, and encrypted if necessary. This is the job of the application layer protocol within the TCP/IP model, but this includes the functionality described by the application, presentation, and session layers of the OC model. The application layer sends this data as a stream to the transport layer. Then segmentation and initial encapsulation. This step, segmentation and encapsulation of the data, passes down the protocol stack. First, the transport layer. The HTTP GET message will be broken down into smaller, more manageable pieces, and each part of the message will have a transport layer header added to it. Inside the transport layer header are indicators on how to rebuild the message. Also included is an identifier port number 80. The next step is the addressing. Address identifiers are added to the segments. The network layer accomplishes this by encapsulating each segment within an IP packet header. The IP packet header contains the IP addresses of the source and destination devices. The combination of the source and destination IP addresses with the source and destination port number is known as the socket. The socket is used to identify the server and service being requested by the client. The fourth step is preparing for transportation, and the fifth step is transporting the data. When the data is transported through the Internetwork, it may travel across several different media and network types. The network access layer specifies the techniques for getting the frame on and off each medium, otherwise known as the media access control method. If the destination host and source host are not in the same network, the packet may be carried across many networks, on many different media types, and through many routers. As it passes along the network, the information contained within the frame is not altered. At the boundary of each local network, an intermediate network device, usually a router, de-encapsulates the frame to read the destination host address contained in the header of the packet. Routers use the network identifier portion of this address to determine which path to use to reach the destination host. Once the path is determined, the router encapsulates the packet in a new frame and sends it to the next hop on its way toward the destination end device. And finally, the last step is delivering the data to the correct destination application. The encapsulation and reassembly of the data occurs as the data is passed up the stack in the destination device. This data is continually passed up the layers, from the network access layer to the network layer, to the transport layer until it finally reaches the application layer and can then be processed. But how can the device be sure the correct application process is identified? Each application of service is presented at layer 4 by a port number. A unique dialog between devices is identified with a pair of layer 4 source and destination port numbers that are representative of the two communication applications. When the data is received at the host, the port number is examined to determine which application or process is the correct destination for the data.
He came with a message, with a protocol all his own. Came to a world of cruel firewalls, uncaring routers, and dangers far worse than death. He's fast, he's strong, he's TCP/IP, and he's got your address. Warriors of the Net.
Thanks for watching.